Hello, this is the first video in the series of atomic and molecular spectroscopy, and we are going to start off with the topic of Bohr-Sommerfeld theory of hydrogen atom. Now, this term that I used, spectroscopy. Now, spectroscopy is definitely a study which helps us determine the substances by means of the wavelengths or the spectral lines. Now, how are these spectral lines produced? Well, the electric currents or even uh, different frequencies of wavelengths, with different frequencies and wavelengths, monochromatic lights, when they are made to pass through a given substance, then the electrons which constitute the atomic structure of it, they get excited, and upon de-excitation, that is, they get excited to a higher state and then they come back to their ground state. The de-excitation thus caused produces spectral lines, and these spectral lines then are studied, and they are of specific wavelengths. They are line spectrum because they are discrete wavelengths which are obtained, but there can be continuous forms as well, but that is a separate thing that we will be discussing. But as of now, what we need to know is that these discrete lines, the collectively known as the spectral lines, they help us, they make spectroscopy a very useful tool for chemical analysis of different substances which are unknown to us. So the line spectrum that we obtain, the atomic spectrum, they are investigated. Okay. Now, going back to the early stages of detection of spectral lines, the line spectrum of hydrogen atom was observed, and initially that was observed by Balmer. The field line that Balmer observed, the wavelengths that were associated with these lines, there's no actually field lines, but they are obviously bright lines which were obtained. So this is how the lines were placed with some gapping in between them. Now this that I'm drawing in front of you right now, this is a highly magnified view. Obviously the line spectra is not like this. On the contrary, that the shades that I am drawing, they are actually the bright shades which are obtained in dark background. Here it's the other way around as I'm sketching it for you. Here it is the bright background and the dark shades, but it's just the other way around. So these are some of the wavelengths that was associated initially. This is the, because for the hydrogen spectrum, so this was the H alpha, and then we had the H beta, H gamma, and H delta, and so on till they reached a series limit. Okay, the series limit was the infinite line, but that's of course having some wavelength at the end. If I am supposed to write the wavelength, then this is 6563 angstrom units, and 1 angstrom being 10 to the power minus 10 meters. So this is 4861 angstrom. This one's 4340, and this is 4102 angstrom. Likewise, it continues, and the lines obviously, the gap between the lines gets narrowed, and finally you have this final line at probably 3646 angstrom units. And Balmer just gave an empirical formula in 1885. He had obtained these things, and the empirical formula that he came up with had the value for wavelength to be equal to 3646, that is this one over here, times of n square divided by n square minus 4, and n square, n here being the value where n is equal to 3 for this line, n is equal to 4 for the next one, and it continues, n is equal to 5, n is equal to 6, and it continues likewise. So the value of n starts from n is equal to 3, and then it continues as such. So this is the formula. Now this was however more generalized by Ritz and Rydberg. The formula that was generalized by Ritz and Rydberg, they gave a more general formula, which is the wave number, which is the reciprocal of the wavelength, that is equal to some constant RH times of 1 by 2 square minus 1 by n square, where n again here is 3, 4, 5 and so on for higher lines. Here RH is the Rydberg's constant. RH being the Rydberg's constant and has the value 1096,7757.6 meter inverse, and this is what they ended up with. Now this was confirmed by Bohr's model and Bohr's postulate. Now at this level uh, we must have come across these postulates where it is stated that all the electrons that are revolving around the nucleus, they revolve in circular orbits first of all, and then they have a fixed state in which, or fixed orbit in which they move around the nucleus, and they are the stationary orbits or the ground states of the electrons. And then they are they can be excited from those ground states, and they can momentarily move over to a higher state where they come down back to their ground state with some spontaneous emission, and that emission is in the form of radiation which has a certain frequency associated with it, and also that the angular momentum of the electron which is revolving around the nucleus, that remains quantized, meaning that it must have specific values of angular momentum and not anything between that. So the quantization concept and all of that under Bohr's model of atom, we won't be going into the detail because that is in the secondary level, higher secondary level, and that has been discussed in a separate video altogether. So here we have R, the radius of it. Well, I'll be just writing down the certain values that are obtained, so just showing the quantization part of it. So R is equal to n square h square epsilon naught divided by pi m z e squared. Now here all the symbols, as you know, have their own meaning. The n is the quantization, the principal quantum number, h is the Planck's constant, epsilon well, it's epsilon naught is the permittivity, and pi is just a constant number, 3.14, 22 by 7. Mass of the electron as m, z being the atomic number of the given atom, and here E is the charge of an electron, 1.6 times of 10 to the power minus 19 coulombs. Uh, the speed with which the electron revolves around the nucleus, even that is quantized, and that is given by Ze square 2nh epsilon naught. The kinetic energy is Ze squared divided by 8 pi epsilon naught r, and the potential energy being negative for the electron being in the bound state as it moves about the nucleus. And so the total energy is simply the addition of the kinetic and the potential terms, and we have it to be equal to Ze square, that is the negative of the kinetic energy, or half of the value of potential energy, as you know from the higher secondary level. So this is more or less the outcome of Bohr's model. We have a more generalized form in terms of the quantization or quantum number, and that being minus mz square e to the power 4 divided by 8 epsilon naught squared h squared, and all of that multiplied to 1 by n square, telling us that E varies inversely as the square of n being the principal quantum number once again. So these are some of the formulas that they had obtained, or that was obtained from Bohr's model. Now what about now comes the other feature, or the other direction, or other view, so as to say. The these are the quantized states, but what about the unquantized states? Now, we haven't really considered anything unquantized in Bohr's model, but in fact Bohr's model doesn't deal with non-quantized states. What happens in unquantized state is what we will be discussing right away. Electrons, they are simply clouds of electrons which are moving around the nucleus. So this probably is the nucleus. This is the expected orbit around the nucleus, the circular one, as per Bohr's model. But it may so happen that with the electron cloud around the nucleus, it may so happen that an electron may be taking this parabolic trajectory. It may be moving with a speed v along this parabolic path. Elliptical, not parabolic, elliptical. Well, in that case, what happens is that the electron here is in an unquantized state, but it is not supposed to be there, because Bohr's model stands valid to a lot degree. So in that case, what happens is that this unquantized electron, it tends to shift from the unquantized state. It shifts to the quantized state. As a result of that, what it does is that it gives away some energy because of this change, because it moves from one orbit to another orbit, one being elliptical and the other one being circular. So in that case, what it does is it releases some energy, and that energy, as we know from Bohr's model, is some Planck's constant multiplied with some frequency. Here the frequency, let it be nu prime or nu dash, and this will have a certain value, because the total energy initially was the sum of the kinetic and the potential energy, which is what I am writing right now. This is the sum of the kinetic and potential, and remember, the potential energy is negative for the bound state, and that is why it is a negative, but it is being added to the kinetic energy, and minus the potential energy, or the energy that it possesses. So minus of this energy, because that's also in the bound state, this will be in minus mz square e to the power 4 8 epsilon naught squared h squared. Well, this energy, we had discussed it, isn't it? This is for the quantized state, and this is for the unquantized state, when it is moving with a velocity v, or with a speed v, and with a distance r between the nucleus and the electron. Now this v and this r, it keeps on varying, and that is why this frequency will be having different values, because the velocity or the speed of the electron changes, because it is moving along an elliptical path, and from that it is shifting. constantly, and the radius or the distance, not the radius exactly, but the distance, the potential energy term carrying the distance in the denominator, that is also changing, and that is why h nu prime, especially nu prime, will have variable values. Now, with these things available to us, but however, uh, we can stick to the Bohr's model where we have the quantized states, right? Because these variations will be very negligible. Okay, now we move over to a separate discussion, which is absorption spectra. What do you mean by the term absorption spectra? Obviously, it's just the opposite of the emission spectra. Now, absorption spectra, because the emission spectra are bright lines which were obtained over a dark background. Uh, the absorption spectra, they are discrete dark lines. Okay, they are discrete dark lines which are obtained for an emitted, for a provided light source, continuous light source, which is provided to a setup. Let us suppose what happens is that if hydrogen gas kept in atomic form, if it is placed in a glass cell, right, in atomic form, if it is placed in a glass cell, and continuous light is allowed to is made incident on it, and then it is captured over by a spectrometer, then this spectrometer, what it detects is it detects these dark lines. They have the exact frequency of emission lines. They were observed to have. Okay, and these dark lines are not completely dark. And no Balmer lines are obtained, are observed in this absorption spectrum. Now we have a reason for all of these things. Now, what is the case where it is having an exact frequency as that of the emission spectrum? Now, what happens in this case is that as these continuous source of light is made incident on these atoms, the electrons, they tend to move, or they absorb these uh, the energy from these light source, continuous light source, and by absorbing the energies, they straight away jump to the higher orbits, right? And but as you know, if they move over to the higher orbits, they just get back to their ground state, almost spontaneously releasing emissions. So because the difference between the energy levels is specific, as we have obtained in Bohr's model, because the energy levels are varying as 1 by n square, so that is why they are discrete levels of energy. And when these electrons, they absorb the energy, they move over to those lines, those levels, and they will be requiring exactly the same amount of energy that they would have required while coming down, or that they would have given out while coming down from those excited state to the ground state. Let me give you a demonstration for it. So this is an electron over here. It is getting some energy in the form of light, and it requires a certain specific energy and it moves up to this level, higher level, but spontaneously it comes down, emitting this radiation. Now, this energy obviously is the energy required for it to go from this to this, and this is an incoming light from a source, and because it has taken up this energy, this light that is absorbed, now taken up by this spectrometer, after passing through this, the spectrometer detects a void in it because the energy has been taken up, and that is why you have those dark lines. However, it spontaneously comes down, and that is why it gives away this emission spectrum, and that is why it is not completely dark. So we have both the reasons, both the statements that we had over here, both the phenomena that we observed, we have reason for that. The what happens initially, it absorbs a certain frequency, and that is why those lines are missing, and that is why you have these dark lines, and then it spontaneously gives out. But there is some darkness, because had it given out this complete radiation almost spontaneously, whatever was lost over here is gained over here, so there wouldn't have been any dark line in the first place. But that is not the case. You see, these electrons, they may jump over to a very high orbit or very high level, and as they come down, they may not be coming down directly, they may be coming down over here in this level, and then from that level they will be coming down to this level. So not always do you have a direct transmission from the higher to the lower state. In that case, it would have filled this void that it was getting. The dark places would have been completely brightened and you wouldn't have observed any difference. But that is not the case. It takes some time. It may come down in steps. And what about the Balmer lines? Well, initially, what happens is that these electrons, they are always in case of hydrogen, that is, they are always in the ground state where n is equal to 1. So the absorption can occur only from n is equal to 1 to n is equal to something greater than 1. So from n is equal to 1, it will go over to n is equal to, which is greater than 1. And because of this, all we have is the Lyman series, because from any higher value it will be coming down to the n is equal to 1 state. This is for hydrogen especially. Now, in some of the stars, okay, in some of the stellar atmosphere, there is the temperature is pretty high, and the sufficient number of hydrogen atoms, they can go over to the first excited state, that is n is equal to 1. This is the first excited state. The excited symbol is usually in form of star. So this is the first excited state where n is equal to 2, and because of high temperature in some stellar configuration, stellar atmosphere, they have these higher temperatures. As a result of that, that's in the excited state. So there the Balmer series have been observed, okay, and this Balmer series has helped us in a way, because from the Boltzmann probability distribution, which gives us a ratio between the number of electrons which are having an energy E2 in a given temperature to that in E1 at that particular temperature. From that, you have the value to be equal to e to the power E1 minus E2. This is difference in energies divided by kT. So this helped actually to determine the temperature. of these stellar atmospheres, and that was calculated with the known values of Boltzmann constant, and with the energy levels, already the values being constant as determined by Bohr's model. The temperature that was obtained was nearly equal to 10 to the power 5 Kelvin. So this was somehow helpful in determining this temperature. And then we have the final bit of this video for today, that is a discussion on a resonance line. Resonance line, well, this thing that we discussed over here, that is what is going to give us detail about the resonance line. Now, well, I said that it takes place in steps, because as it moves over to a much higher orbit, it a much higher state, it comes down in steps. Now that is okay, that is known as that those different frequencies that are obtained in that case, that leads to atomic fluorescence. The phenomenon is known as atomic fluorescence. Okay, that phenomenon is known as atomic fluorescence. But if this excitation occurs between two specific states, the immediately above state, then we obtain, because the frequencies match, because this frequency that it has taken up is the same as this frequency that it emits, this line that we get is what we call as resonance line. Now this was the initial part of the Bohr-Sommerfeld theory related to uh, spectroscopy. We'll be we'll be going into more details of it, but that is for the upcoming videos. Till then, thank you for watching.